Hello, my name is Steve Diaz da Cruz and I'm the first author of our paper. In our work, we focus on changes in the illumination and environment and its effect on the robustness of machine learning models. We propose a new normalization strategy for post-processing based on encoder-decoder models. Moreover, we release a synthetic dataset for the vehicle interior. The performance of many machine learning algorithms suffer from changing illumination conditions. Consequently, images in different weather conditions, date times, and seasons need to be recorded in order to assess the model's reliability or improve their robustness. Some papers discuss this effect on semantic segmentation, localization and classification, place recognition, and 3D human pose estimation. An existing work on portrait shadow removal proposed a method to remove shadows by relying on prior information. The authors exploited the symmetry of human faces and the detection of facial landmarks. Consequently, this method is limited to facial images only. Other papers on shadow removal managed to remove rather simple and dominant shadows from images. They used shadow and shadow-free image pairs, or even shadow masks, to train their models. However, this is not possible for more complex scenes, and illumination conditions for which a ground truth is not available or even impossible to define. Based on the Zero dataset, we created images for 3 new vehicle interiors. For each vehicle, we created 250 training and 250 test sceneries, where each scenery is rendered under 10 different illumination conditions. Each seat position can be empty, occupied by adults, children in child seats, or babies in infant seats. Our method relies on having the same scenery under different illumination conditions. For each scenery, we randomly select 2 images. The first one is being used as input to the encoder-decoder network, and the second one is being used as the target image to measure the loss with respect to the reconstruction. This formulates a partially impossible task to solve. The input image does not provide all the information necessary to reconstruct the target image in its entirety. While the objects are the same, the illumination and background changes, such that the objects appear in different lighting conditions. The only possibility for the model to reduce the loss is to learn implicitly to average out all the illumination. On the left-hand side, the model can remove all illumination and background information from the training samples. However, this approach does not work reliably on test images, as you can see on the right-hand side. The blurry reconstruction is a blurry version of the nearest neighbor in the latent space. In order to improve the reconstruction on test images, we adapt the loss function of our encoder-decoder model by adding a triplet loss in the latent space. The anchor image is processed as before. Then we select the positive sample to be of the same class as the input image, meaning the same objects occupy the same seat position. Then, for the negative sample, we select an image for which the occupancy only differs in a single seat position with respect to the anchor image. The triplet loss induces an L2 norm in the latent space, such that the nearest neighbor search is more meaningful. By reconstructing the nearest neighbor of the latent space vector of the input image, we can achieve a class-preserving reconstruction. The label of the nearest neighbor can then also be used as a classification prediction. Combining the partially impossible reconstruction loss with the triplet loss and nearest neighbor search, we can achieve good results on the test images as well. In order to measure the success of our proposed method, we compared its classification accuracy on the 3 vehicle interiors against commonly used classification models. Our approach outperforms all pre-trained classification models when fine-tuning them on our dataset. Both the partially impossible reconstruction loss and the triplet loss together with the nearest neighbor search yield the best results. Additional results and an ablation study can be found in our paper. On the extended Yale face database, the model can remove shadows and normalize the illumination on the faces seen during training. As before, the reconstruction does not work reliably on the test images, and the faces often appear blurry. By using the triplet loss and selecting the nearest latent space vectors, we can reconstruct similar faces with similar head poses. Finally, on the Webcam Clip Art dataset, the model removes the illumination and shadows from the input images. Moreover, the skies, sand, and rivers are smoothed out. Vehicle and people are removed and replaced by the background. Thank you for your attention, and please visit our Q&A sessions for questions and discussions.